Şimdi okay, so let's remember what we did last hour, cache organization, and then I will solve a example. So we said that there are three types of cache organization, cache mapping methods, functions. And according to the given address that the CPU is trying to access, a block is accessed, a block is moved into the cache. So which block will be selected from the cache depends on the given memory address, but where it will be mapped in the cache depends on the mapping functions. Let's remember the rightmost bits in a block address, in an address, the rightmost bits in an address gives which word it is in a given block. So if in a block there are 4 words, then you need 2 bits to address those 4 words. And those bits are from 0 to 3. And the rest, leftmost bits, are all the same for all the addresses in the same block. So for the leftmost bits are all 0 for block 0. And these are the words in that block. For block 1, leftmost bits are 1. These are the words, numbers in the given block. So in direct mapping, the first one, each block has a specific place in the cache, and that is determined using the mode operation. So more than if there are, let's say, 4 words, 4 lines in a block, then you take the mode of 4, you take the block number, J is the block number, and you take its mode to 4, and you find which cache line it is mapped. So in a given memory address, so assume that this is the address that the CPU is trying to access. There are 4 words in a block, so the rightmost 2 bits show the word number. Then there are you remember, in mode operation, in binary numbers, it is easy because we are taking the mode of 2, 4, or 8, powers of 2. Therefore, the remainder, for example, the block number is this, and the remainder with respect to 4 will be 1, because the rightmost 2 is 4 is 2 bits. If you just take 2 bits from the block number from the right, you find the remainder with respect to 4. So the next 2 bits afterward on the left 2 bits are line number. So it means that this block will be mapped to line 1. It will be mapped here, and the rest is used as tag because more than one block mapped to the same line. So this tag field determines which block is it in the cache. So the CPU first checks this, first goes to this line, compares the tag with the tag in the cache. If the tags are the same, this means that this address is already in the cache. So using the word field, access only that word, access only word 3, and send it to CPU. This is the hit case. The miss case is if the tags are different. In that case, this means it's a miss. The block is not in the cache. So take the block from the main memory into the cache, all these 4 words, and place it to line 1 and change the tag. The previous block here is lost. So we said that the advantage of this method is each block has a specific line to map in the cache. So therefore, the comparison circuit is simple, but the disadvantage is if two blocks that replace each other are continuously accessed one after the other, then this is a disadvantage, because even to access one word, you take the complete block into the cache, which takes a long time, and then it is replaced by another block, again for only one word. So that was the disadvantage of direct mapping. To eliminate that disadvantage, we said that there is associative mapping. In associative mapping, any block can be mapped to anywhere in the cache. There isn't a specific place. A block must be searched, therefore, in the whole cache. So in this case, in our example, block 2D and 01, in direct mapping, we're replacing each other continuously. But in associative mapping, block 2D, when it is first accessed, is taken into the cache. Block 01 is also placed in the cache to another line. So they don't replace each other. Both of them can exist on the cache. Here, the tag, there is no line field is used in the address, because a block does not have a specific line. It can be anywhere in the cache. So the whole block number can be used as the tag. But in this case, a block can be, when we're looking for a block, when we're looking for an address, is it a hit or a miss? We have to search all the tags in the associative memory. We have to compare all of them with the given tag. So that must be done, obviously, in a very fast way. So you need a hardware to do it. And that hardware is actually an associative memory, which compares each bit in the stack with all the bits in the tags of the cache in one step. So this comparison hardware is more complex than direct mapping. Therefore, the size as you need in a specific area, you have to use some of that area for this comparison circuit. Therefore, the size of the associative memory cache, associated map cache cannot be too large. But it has the fastest cache type. Now the third one was set associative mapping. Here, again, direct mapping method is used. So there are sets in the cache, and each block has a specific set number, like direct mapping. For example, here there are 4 sets in the cache. Block 0, block 4, block 8 will all be mapped to set 0 because their mode is 0. Again, block 1, block 5, block 9, all mapped to set 1. But different than direct mapping, in the same set, there are more than one line. So if we place block 0 to set 0, and then if the CPU accesses block 4, it is also mapped to set 0, but it can be placed to the other line. So therefore, both blocks that map to the same cache set can exist in the cache. So that, therefore, they will not replace each other like direct mapping. They can both exist in the cache, so that improves the performance of the cache system. And in today's cache architectures, set associative mapping is a frequently used method. It may be a 2-way or 4-way set associative mapping, or it may be a k-way set associative mapping. So what will happen if Okay, if the CPU is trying to this address, now there is a set field in the address, not this one. And using that set field, the block is accessed on only in that set, but it can be any one of these lines. It may be in line 0 or line 1. So only the tags of these sets are compared. So the comparison circuit, therefore, is not too difficult like associative mapping, because in associative mapping, all the tags in the set, in the cache, must be compared. But if it is a two-way set associative mapping, only two tags have to be compared with the tag in the address. Therefore, the circuit is not too large, but also one advantage is that the second advantage, both the blocks, they can exist in the cache, so they don't replace each other. That improves the performance.
Hocam burada ben şey sorabilir miyim acaba?
Tabii.
Cache'de tag data ve V harfi vardı. O V'nin anlamını tekrar söyleme şansınız var mı? Kaçırım galiba.
Valid bit, yani bilgisayarı ilk açtığınızda bütün yani orada bir sıfırlardan birlerden oluşan ama bizim için valid olmayan bir bilgi var. Random bir şey var. Onun için valid bit 0 ilk açtığınızda bilgisayarı. Ama oraya bir data getirdiğinizde, bir blok geldiğinde oraya valid bit 1 oluyor.
Tamamdır hocam. Çok teşekkür ederim.
Ama ondan sonra hep 1 olarak kalıyor. Yani kapatıncaya kadar tabii. And when the cache is full, we said that there are methods when the cache is full in associative mapping, when the cache is full, or in set associative mapping, when both lines are full. Let's say 2D is here, block 01 is here, and another block that maps to the same cache set comes. One of them must be replaced. It must be written either here or there. But which one? That is determined according to the replacement algorithms. We said that one replacement algorithm is random replacement. Randomly it selects one of them. The second one is first in, first out. In first out, the one that is brought into the cache for the first time, that is replaced. So the one that has been longer in the cache is replaced. So that is easy. Assume that in our case, 2D comes into the cache, then comes block 01. In that case, block 2D will be replaced because it is the first one into the cache. Now, the other two may be a bit confusing. Least recently used method. In least recently used, chooses the block which has been in the cache longest with no reference to it. So you take it into the cache, but for a long time, you don't use it. In that case, you can replace it. If you have two lines in the cache, if it is two-way set associative, in least recently used, you use a use bit. There is a valid bit and you add a use bit. So when you use a block, you make it 1. It is two-way set associative. So the one you use, you change the use bit to 1. The other one becomes 0. So in this case, the recently used block has use bit 1. The other one has use bit 0. So when you are going to replace it, which one would you replace? Not the recently used, least recently used, which has use bit 0. You will replace that. Now let's check this example. What will happen? This is the final state. Block 2D comes into the cache. You access it. Okay, let's have this example. The program accesses B7. B7 is mapped into the cache. It is in block 2D. Right? So block 2D comes into the cache, this one. And then it is accessed again, block B7. Block B7 again in 2D, it is accessed for the second time. So when it is first taken into the cache, use bit becomes 1. This is 0. Again, you access the same one in the second line. Use bit becomes 1. The other one is 0. And then it accesses block 04. It's address 04. It is in block 01. So this line has invalid bit, so it is placed here. Now the recently used one is this. So its use bit is 1. And the other use bit becomes 0. And when another block that maps to the same cache line comes, it is block 21, which one will be replaced? The recently used one is block 01. So least recently used will be replaced, which has use bit 0. That will be replaced, and block 21 will be placed here. Do you agree with that? Efendim? Evet, bu 1 olacak. Use bit'i 1 olacak. Öbürünün ikisi bu olacak. Çünkü tag değişecek tabii. Tabii. Bu 2D'nin tagiydi, o da değişecek. Buraya kadar tamam mı arkadaşlar? Online'da bir soru var mı? Ses gelmiyor hala mı? Duyuyor musunuz? Tamam. Eski mesaj demek ki. Peki. Buraya kadar bir sorunuz var mı? Yok gibi. Tamam. Şimdi ara vermeden önce şu least frequently used'a da bir bakalım. So in least frequently used, the frequency is important, not the time. In least recently used, the time is important. If you don't access a block for a long time, you can replace it. In least frequently used, the frequency is important. If you access a block very frequently, it must remain in the cache. If you don't access a block very frequently, you can't remove it. So it replaces the block which has experienced the fewest references. In that case, you need to use a counter for each cache line. Again, assume that B7, 04, and 86 are accessed. So B7 is in block 2D. It comes into the cache. It's bir dakika, diğer, evet burada. So here we have the counter. B2D comes into the cache. Its counter is 1. It is accessed once. And then load B7, again, it is in block 2D. So the counter becomes 2. Now comes load 04. It is in block 01. Counter becomes 1. Now load 86. 86 is not in the cache. Which one will be replaced? Block 2D has a higher counter, so it is frequently accessed. Block 01 will be replaced, and block 21 will be placed here. Do you follow? Any questions? Any questions from online? Okay, so these are all read policies. And the data is in the cache, in the main memory. The data is in the main memory. In order to access it, we take it from the main memory into the cache. This is a read operation. And load is actually a read operation, you remember. You read a value from the memory into the CPU and place it in the accumulator. But there's also store operation. Store means you take the value from accumulator and write it into the memory. And in that case, it's a write operation, memory write operation. Now, the problem in memory write operation is the problem here is if you have only main memory and CPU, there is only one copy of the data. And that is in the main memory. If you don't have a cache, there's only one copy of the data and it is in the main memory. So what you read or write is to the main memory. But if you have a cache, there are two copies of it. You take it from main memory into the cache and also to the CPU. So the same data, the same block has two copies. But if you are going to update that block, will you update the cache? Or will you update the main memory, or will you update both of them? That is the problem. And to solve that, there are basically two policies, write policies, we call them, write back and write through. And the two things are important here. One, the copies must be consistent. Two, it must be fast. So write back makes the system faster. Write through makes the system consistent. The two data values in cache and main memory are the same in that case. Ara vermek istiyor musunuz? Evetleri görebilir miyim? Hayırları görebilir miyim? Verelim mi yoksa devam edelim mi? Yoruldunuz mu? Hadi verelim bir 10 dakika ara. Ondan sonra çünkü bu yeni konuya başlayacağız. Biraz uzun sürebilir. Arkadaşlar 10 dakika ara verdik.